Quadruple 101.
Wow, really? Welcome to the Sandy Hill Institute of Technology. So what do we have for our knowledge-hungry people today? We have the quadruple. Now, there they are. For those who always wonder, what exactly is a quadruple? That is a quadruple. Actually, this is a quadruple. And it's called a quadruple because it's got 4 rods. So, looking around, they come in different sizes. Here you got 3 of them. 1, 2, 3. This is then the collision cell, and you have 2 mass filters and a detector. This is actually old Finnegan 4500 or something. Smaller version, the ubiquitous Hewlett-Packard GCMS. Ion source, quadrupole, detector. Simple. This, where did we pull that out of? What did that used to be? Q-TOF? Anyway. Quadrupole, collision quad, little lens system. Oh, and this one has a little pre-filter for the quad. Alright, so how do they work? There's a lot of stuff about that on the internet. Most of it doesn't make any sense. Here's the bottom line. So you have these 4 rods. Did I bring a pen? Yes, I did. You have these 4 rods. So here they are. 1, 2, 3, 4. Now you're going to connect these 2. Where do you see that here? The opposite ones are connected with a piece of copper wire. So I'm going to call those 2 plus, and I'm going to call those 2 minus. So these are connected. Now, why is this thing a mass filter? Well, normally when these things are in an instrument, there's like a little plate in front with a hole. So it's something like that. So there's your hole in, there's your hole out. So, first point to note, only ions that, if you go in through this hole, the only ions you're going to see after that are the ones that come out at the other end. So, anything that gets thrown off axis will not come out. And that's the critical thing about how these quadrupoles work. So, what you do with these things is you put on the opposite rods, you put a radio frequency or RF voltage, usually about a megahertz, with a certain amplitude. And you also put a little bit of DC on it. Now those 2 together, they start doing complicated interactions on the ions. Now, if I'm an ion, and I'm in here somewhere, and I see this field polarity changing all the time because of the RF, it's going to be pulling on me. If I am a tiny weeny little ion, I will have no problems following that. And so every time I go through this RF motion going back and forth like that, I pick up a little bit of energy out of the field. So I start wandering further and further off where I was, and I don't make it out of the back hole. I did not mention something. When these ions come in, they have a little bit of speed, not a lot, a couple of volts, maybe 15, 20, 10, 5. So they do have a little bit of, they have velocity in this direction. Alright, so yeah, the light ones, they get kicked off by RF pretty easily. Now if I'm a big heavy one, you know, these oscillations go way too fast for me to respond, so it's not going to affect me that much. So I'm going to come out at the other end because I haven't been thrown off course a lot by this. Now the DC, what that does is it actually starts a slow drift, and the combination of the 2 makes that if you were to draw a graph of mass here, and the ratio of RF over DC. So the ratio of RF amplitude, okay, it's about amplitude. Frequency's got nothing to do with it, at least not with the filtering. Then each ion will have what they call an area where it's stable. They call this a stability diagram. There's an awful lot of math involved in figuring all of this out, but that's what it boils down to. So, you know, so what this shows is that there's a mass region and a RF over DC region, which makes these things come out, and it makes it pass. And so the mass over here will not pass, mass over there will not pass. Now, one thing that comes out of this picture also is if I go and sit right here, my transmitted mass range is really small. So that's high resolution. Now, the thing that you never see in these drawings is if I do this for a couple of different masses, right, then the next one is going to be there. One mass down and one mass up is going to be there. So this is it. The ratio of RF over DC determines which mass you transmit. And now I'm thinking, is there any way to make this clearer? But most pictures of the stability diagrams that I've seen, they don't show you, they only show you one mass. But you know, this is the trick, like it does this. So I can scan, in other words, if I vary the RF over DC in time, I actually get a mass scan. And well, yeah, that's it about quadrupoles. Now, size, does it matter? They say it doesn't, but I've heard different. I have heard that size matters. So, so the resolution is basically has to do with how well you tune the electronics to. Now, it's tricky though, because if you go a little bit too far, you get absolutely nothing. So the region between, oh, I got really good resolution now, and shit, I'm not seeing anything, is very, very small. So because they don't want these instruments to fail, they usually go and sit a little bit lower than that, so that, you know, you have a little bit of slop and you're not in danger of losing your ions altogether. Okay, now if you have a closed quadrupole like this, you could put gas in it, right? Now, the thing about, oh, let's get back to different modes of operation of this thing. Suppose I just had the RF going, no DC at all, then it essentially becomes a low pass filter, a high pass filter, right? Because only the high masses will pass. Isn't that something out of, what was that? Only that's the thing with Indiana Jones. Who was going to pass? Only the humble will pass, or something. Anyway, it's something like that. So, like over here, you got a tiny little quad. It's only that long, and it's fed with capacitors. So, okay. So, this is what they call an RF only quad, and really what it does is it doesn't do any mass selection. It just, you know, kicks out the really low ones. Depending on where you set it, you know, you can the high masses will always go through. It acts actually more like an ion guide than it does act as a mass filter at that point. So, but you know, you got a little pre-filter, you got quad. Now, so the longer this thing is, the more time the ions have to start listening to the field. So the implication of that is that if my quadrupole is longer, my voltages can be a little lower to get the same effect, because now I have more time to do it. So it also affects, I mean, ultimately your mass range is determined by how high can you go with these voltages, and there's a limit somewhere. You know, about 2-3 kV, and you've had it. That's kilovolts, so that's don't go poking around in quadrupole RF supplies. They can be absolutely lethal. But so it's a trade-off, you know. Also the distance between the rods, I mean, it's way larger here than it is there. Now, so what that means is, now if I put my rods further apart, I'm gonna need more volts for the same field strength. So all of this stuff goes into the design, and what you ultimately want to come up with is a happy medium between what is easy to do and gives you the best kind of performance. So mass range typically of a good quadrupole, 4,000 or something like that. That I'm looking at and I'm going, meh, a couple of hundred maybe. Something similarly sized is in this little HP MSD. How high did they go?
614 with the calibrant.
Oh, well, okay. So, yeah. Now, is there anything else we should be saying about quadrupoles?
Mass selection is done where in that little triple quad that you have?
Oh, in this one? Well, it depends. If you say, okay, I'm going to tune this one to a mass, and I'm going to only pass mass 100.
So in that incident, you would be setting the voltages
Well,
in
yeah,
the diagram
if
to sit at
mass
the top.
100 is here, then, you know, my ratio is there, so I would set my stuff.
So it probably actually sets it more somewhere down here, because we know that the resolution isn't great.
Well, wherever you, I mean, that the slope of this line is determined by the electronics, right?
Right.
And then from that point on, it's just one derived signal says, okay, you know, I want you to go here mass-wise, and the RF and the DC, the ratio between them is determined by the electronics, so you don't need to do anything about it. Because, you know, sometimes they have what they call a resolution setting, or different people call it different things, but it allows you to play with that ratio a little bit up to a limit. They usually do it such that no matter what you do, you can't completely fall off the peak and lose your signal totally. See, now I forgot what I was talking. What was I talking about?
Don't know.
Oh.
So that's
Oh, yes, I remember now. It's all coming back to me. Isn't there a song about that?
Mm-hmm.
Anyway, so if I tune this guy to, let's say, mass 100, because it's a nice number, there aren't many ions at that mass, but never mind, mass 100. I put collision gas in this thing, so I only have mass 100 coming into this collision quad here now, and it's going to get banged up by the gas and fall apart. The fragments of it, I can then, if I scan this guy, like go through the entire mass range with this guy, I can look at all the fragmentation products of that mass 100. So that's what they call MSMS. So this one's stationary and only lets through one mass. That one's doing the colliding and making the ions very unhappy. So unhappy actually that they fall apart. And this one then analyzes the product, so this one scans over the mass range. And then that little trumpet down there detects the ions. And I don't think the official name for that's trumpet.
No,
Wasn't it like a continuous dynode electron multiplier?
it is.
Trumpet!
Channeltron.
It's a trumpet. All right.
Okay, excellent. That
Done.
is Quadrupoles 101 with Sander Monmouth.
It's
Thank you,
201
Sander.
actually. We did one before, but I didn't like that. I don't think I explained it. Maybe I explained it a little better now.
This has diagrams.
I drew
have
something.
diagrams.
I did draw something the last time.
That's right. Thank you, Sander.
You're welcome.